Everyone, and welcome to this theory prep video. Today we'll be talking about asymptotics, which are sort of a way of measuring runtime. We'll see some more complex definitions as well today, which should be a good exercise in practicing skills we learned a couple weeks ago about how to read a definition and make sure you really understand the intuition behind it. So let's start with just a question of how fast does an algorithm run. Let's say we have some program P, then we can represent the runtime of the program as a function. So we'll have function f of n, where n is some natural number, be the runtime of program P on an input of n bits in seconds. And the reason that f is dependent on the number of bits that it takes in is you can think about, well, if you have more bits, you're basically putting in like a larger input. So thinking about like the 3-SAT or the graph theory problems that we talked about last week, like if the graph is bigger, or if the 3-SAT equation is longer, like those are just necessarily going to take longer. And if the input is shorter, right, then it won't take as long. So we want to make the runtime of almost all programs really depends on their input length, or at least sort of gets longer as the input length gets longer. And so we capture that by having f taken the natural number of the number of bits in the input as the argument. And so below I've written just like some possible runtimes, right? You could have like f of n, if you put in inputs of like 10 bits, then it takes like 10 seconds to run. But a relevant question is like, what if you just like switch to a new computer and your computer is like twice as slow? So it's still like trying to do the same thing, but now it takes 2 n seconds to run. Well, which of those is like the true runtime for the program? Like, it's not really clear, right? If you move to a computer that's like a factor of 2 or even like factor of 5 faster, or some constant factor faster or slower, it's unclear like what is exactly the true runtime of that function. And so we're actually going to, when we create our definition for runtime, we're going to take this into account. We're going to say, oh, our definition doesn't care about constant factors. What it does care about is like, if you double the length of the input, like what happens to the runtime? Does it also double? In which case that would be like a linear runtime, right? Does it increase by like a logarithmic factor? Does it increase by an exponential factor? That's what we care about, since we don't have like an exact runtime, right? We are okay sort of up to constant factors. Another thing to consider is like, we're sort of, as computer scientists, we're concerned about the asymptotic behavior of a program. So if we give it really, really, really long inputs, how long does it take? So if you gave it this program like P an input of, like, I don't know, 1 million bits, then this might run in 1 million seconds. And whatever program this is the runtime of might run in, 1,000,004 seconds. But those really aren't that different. Those are basically the same thing. Like 4 isn't a big difference when you get to 1 million. And so that's another thing that we probably want our definition to take into account, right? Like if there are sort of these like other little bits of time that the program takes to do something, but like the main thing that's changing when you increase the input size or decrease the input size is sort of changing in the same way, then we probably want it to kind of classify that as the same runtime. And this is all like really nebulous. I think the key takeaway here is like, these could all be the runtime of a program on different machines, right? This could be the runtime on a really fast machine. This could be like an old one where it's slower, and this could be like, I don't know, maybe it needs some like pre-computational time to like boot up or something, right? But like we would sort of consider those all the runtime of programs. So we would probably want to say, oh, all of these runtimes are like linear, because the runtime of the program should just be like, this thing, not, oh, it's dependent on like, what machine you use and stuff like that. Because as like computer scientists, we're really concerned about like the theory, right? Like the code that's being run, not like the actual like machine that's being run on. So we want to measure runtime in a way that's impervious to constant factors, right? That's sort of a succinct way of saying what we said on the last slide. So we'll define big O as follows. And big O is if we have two functions, f and g, but map from the natural numbers to the positive real numbers, right? So f is maybe the runtime of some program P. Then big O is intuitively saying that f is less than or equal to g. So if f is the runtime for some program P, right, it's basically saying that P runs at most g time, like up to some constant factor, right? And we don't care about constant factors, because if your computer runs twice as fast or twice as slow, like we're analyzing the same program. And So what is the definition? Well, the definition says f is big O of g if there exists some little c and big N such that for any little n greater than big N, f of n is less than or equal to c times g of n. Okay, so there's like a lot of quantifiers, a lot of stuff going on here. So we got to make sure that this definition makes sense. So let's look at each part. The first part we're going to look at is this big N. So basically, the statement that you need to prove for big O only applies to natural numbers that are greater than some big N that you get to pick, right? And that sort of corresponds to the intuition that we only really care about the asymptotic behavior of a program. In other words, we like as computer scientists, we care about as we put like bigger and bigger graphs into this program, what does its runtime look like? We don't care if there are like little sort of small factors at the beginning, and that's exactly what this exist big N is doing. It's saying like you only need to prove this inequality relationship for like really big inputs. And then the second thing is that we have this C here, and it's a little bit hard to explain exactly what the C is doing right now. I think the best way to explain it is that the C is allowing us to have sort of like a constant factor of wiggle room, because even if like g of n is sort of small, then we can still use like a larger C to make this inequality still be true. So I think the best way to sort of exemplify what this C is doing is to try an example. And remember, if you think back to 2 weeks ago, like that was one of the strategies that we had. If you don't understand the definition, try an example. So I'm going to try and prove that f of n is big O of n. So what that means is that like n plus 4 is essentially like linear, right? Like if our program runs in n plus 4, then our program runs in linear time is sort of the intuition that we have. And that corresponds to what we were talking about on the previous page, right? Like all three of these f of n's should basically be the sort of have the same runtime. So we want our definition to work out for that. And the C is going to help us here. So first, I'll choose, just to make it a little bit easier, I'm going to choose big N equal to 5. And then I'm going to choose C equal to 2, right? Because we're proving the existence statement, so we get to pick C and N. And now we have to prove for all little n greater than big N, f of n is less than or equal to C times G of n, right? So f of n is equal to n plus 4, and I claim that that's less than or equal to 2n. And why do we know that's true? Well, we know that little n is at least, is greater than big N, right, which is 5, so it's at least 6. And so that means that like 2n can be written as n plus n, right, which we know because of this is greater than or equal to n plus 6, which must therefore be greater than or equal to n plus 4. And so 2n is just the same thing as 2 times g of n, where g of n is just n. And so we've proven this relationship here. And you'll see basically what this C let us do is, since we could choose C equal to 2, we could let this sort of like second copy of n take care of this extra 4. So in other words, that like this C not only allows us to not care about constant factors, but also it means that we don't really care about like additional like little rough edges on the formula. Like if the main part of this formula, right, like the main driver of this runtime is this n, and that's all we really care about. So now let's apply big O to the other cases, just to really get a sense of how to use it. So first, I'm going to prove that n is O of n. This is a little bit easier. We'll choose C equal to 1 and n equal to 0. And then we see for any n greater than 0, I'm just going to write big N here, but we'll just write 0 because you guys know big N is 0. Then f of n equals n, which is less than or equal to n, which is equal to C times G of n, because in this case, C is 1. And so now we've chosen a C and an n such that this statement holds true, and therefore this statement must be true. So now we're going to prove that 2n is big O of n, And similarly here, we'll choose c equals 2 and n equals 0. And again, we'll see for any n greater than 0, f of n equals 2n by definition, which is less than or equal to 2n, because that's the same thing, which equals c, because c is 2 this time, times g of n. So here you see more directly how this c lets us say not care about constant factors, because this f of n is twice this f of n, right? Like it's like you're running it on a 2 times slower computer. But that c allows us to not care about that 2 because we can just set c equal to 2 and we'll still have the inequality hold. So that's big O. And I think it's important just to think about like, okay, what's the mathematical, technical definition? Then like, does that make sense? Like what are each parts doing? Why do we have each of these variables? Why can't we just take it out and have a similar definition? And then 3, like, does this intuition make sense? Like, do I really believe we shouldn't care about constant factors? Does it make sense that like f of n equals n, or that n and like n plus 4 are both big O of n? And I think just taking some time to reflect really helps you make sure that you understand the definitions. So we just talked about, right, big O, and big O is basically saying like f is less than or equal to g, right? If f represents the runtime of some program P, then f is big O of g is sort of like saying the program P runs in at most g time. But what if we want to prove something else? Like what if we want to prove that f is greater than or equal to g? That's sort of a logical question to ask. And from the perspective of like program P running in time f, like what if we want to prove that program P is like slow, right? Like what if we want to prove it takes at least this much time? Well, then we're going to use something called big omega. So big omega is provided here in definition 5. Again, let f and g be functions from natural numbers to the positive reals. You can think of f as the runtime of some program P. Then we write f equals big omega. This is just the capital Greek letter omega of g of n. If there exists, again, some c and some big N, such that for any natural numbers greater than n, that f evaluated on that is greater than or equal to c times g evaluated on that. So again, remember, whenever you see definition, does the definition make sense? What does every part mean? Well, again, this big N here, right, is capturing the fact that this is an asymptotic relationship. Basically, this is characterizing the relationship between f and g as n gets really big, as n goes to infinity, as the inputs to the program get really, really big. And because it means that we only have to prove the second part for inputs that are of a certain size. And then again, the C is doing a similar thing where it's sort of not making us worry about constant factors and stuff like that. So you can think of this as saying f is greater than or equal to g, right? Because, well, we're saying that asymptotically for inputs that are at least a certain size, f, which is the runtime of P, takes longer than g, like within some constant factor. So then if f is big O of g of n, that's like saying, well, if we go back a couple pages, like that's like saying f is less than or equal to g. And if g is omega of f, then that's like saying g is greater than or equal to f, right? That's what we just said. It characterizes the big omega characterizes the greater than or equal to relationship. So now what we want to do is sort of make sure that these definitions are consistent, right? This is the other thing. So after you made sure you understand all the definitions, just like how we understood like injectivity and surjectivity, then like, oh, those sort of represent like different ways to define like set size comparison. So you should make sure like the ways those correspond to your intuitions about set sizes is consistent with each other. So in other words, like f is big O of g means like f is smaller than g, and smaller than or equal to g, and g is big omega of f means g is greater than or equal to f, right? And those should sort of like be the same thing. So we would expect basically these to be true if and only if the other is true. In other words, we'd expect them to be equivalent. And that's actually something that you'll prove on the problem set. But that's just a good example of whenever you're reading definitions, make sure first to understand all of them, and then make sure like the intuitions that they correspond to make sense with each other. In other words, that they form consistent intuitions. Great. So again, we'll prove some facts with big omega, and this will help us sort of understand the definition again. So first, I'm going to prove that f of n is big omega of n. And the way that we're going to do this is we'll choose c equals 1, big N equals 0. And then, so for any n greater than big N in the natural numbers, f of n equals n, which is greater than or equal to n, which is equal to c times g of n. And that's what we want to show here, right? We get to pick some c and big N, and then we want to show this part, which is exactly what we showed. Now, the other proof is going to be pretty similar. N plus 4 is big omega of n. Again, we can choose c equals 1 and n big N equals 0. And again, for any n little n greater than n big N in the natural numbers, we have f of n equals n plus 4, which is greater than or equal to n, which is equal to c times g of n. Great. So now we've applied big omega in both these cases, right? And so now, if you notice, what we proved n is both big O of n and n is big omega of n. So in other words, so we basically proved that n is like less than or equal to linear, and then we also proved that n is like greater than or equal to linear. And especially if we think of sort of f as the runtime of some program p, like then we're basically proven that like p runs in linear time essentially. So we might want some asymptotic to be able to capture that, which is what we're going to present now. I'm generalizing a little bit, right? If we say like f is big O of g of n, then we're basically saying f is less than or equal to g. And if we say f is big theta of g of n, then we're basically saying like f is greater than or equal to g. So intuitively, like if these were statements about numbers, then we would basically say like f is equal to g, right? And they're not statements about numbers, so it doesn't just like imply that, right? Like these are just sort of these inequalities and equality are just sort of helpful tools to help you think about the intuition behind what these like big O, big omega relationships mean. But we actually do have another asymptotic relationship that we call big theta. And we say, this is a capital theta right here, we say f is big theta of g, or we also say like f is theta of g, if f is big O of g and f is big omega of g, right? And this sort of corresponds to the intuition that f and g like run essentially in the same time up to a constant factor. Note that since asymptotics don't care about constant factors, we get our goal of having all these like fn's be in the same class, right? Like this f of n equals n plus 4, well, it's omega of n. We also proved that it's big O of n, and so that means it's also theta of n. And so if we think of like sort of everything that's in theta of n as being sort of like the same class, right? The same class of runtimes, because they all like basically run in like, essentially what we're saying is they all run in linear time up to some constant. Then n is in that, n plus 4 is in that, 2n is also in that. I left out the proof of 2n being in big theta of n because it's basically the same as the other ones. But that shows that our definition really matches like what we set out to do originally. But it's a little bit hard to understand intuitively what f is theta of g means, right? Like we just said, like if f is big O and if f is big omega of g, then f is theta of g. But what exactly does that mean? So I've drawn a picture below that hopefully helps. So let's say that f of n is big O of n and f of n is big omega of n. Now I'm going to show that like these imply, right, that f of n is theta of n, and so I'm going to sort of give some intuition to what that means. So first, f of n is big O of n, which means there's some like big N, which we'll call n1 because we have two of these relationships, so we're going to number them n1 and n2. So past some point n1, right, f of n is less than or equal to some c2 constant times n, right? That's literally the definition of f of n being big O of n. So that means that f of n has to be like somewhere in this region down here. Then the second thing we say is that f of n is big omega of n, which means there's like some n2, which we've put here. It's possible n2 is like less than n1, right? But then you just sort of like shift this graph over. And past that n2, f of n is greater than or equal to some other constant like c1 times n. And so that means that like, we know like f of n has to be like somewhere in this region here, right? And so it's got to be in both of those regions, which basically means we sort of erase this to make it a little bit less cluttered. Like that means that we know f of n has to be like less than this line and greater than this line, right? So it's got to be like somewhere in here. So it's sort of constrained to be within two linear functions, right? Because it's constrained to be between c1n and c2n. And so that really captures our intuition of like, theta, if f of n is theta of n, it means it's linear. And what that means is like we can sandwich it between two linear functions going out to infinity. And that's good enough for us to call linear. Great. So now we're going to cover one other type of asymptotic relationship. So we've talked about big O and big omega, right? And those sort of tell us like f is like weakly less than g, right? Like f could be sort of the same runtime as g, right? They could both sort of be linear, or f could be faster than g. But what if we really want to prove like, f is the runtime of some program p, and we want to prove that, f is the runtime, p runs like much, much faster than g. Or maybe f is the runtime of p1 and g is the runtime of p2, and we want to prove like program one just runs like faster, basically. Then what we can do is use this definition called little o. So let's go over that. Again, if f and g are mappings from natural numbers to the positive reals because they're mappings from the number of bits in the input to a runtime, then we say f is little o of g of n if for any epsilon greater than 0, there exists a big N such that for any natural number greater than big N, f of n is strictly less than epsilon times g of n. And actually, like this definition would also work even if you put on like a weakly less than symbol there. But we'll just use the strictly less than symbol for this. So now we need to make sure that we like really understand that definition. So we're going to break down each part, and we're also going to think about how is it different from big O of g of n. So going back to the definition of big O of g of n, we see that it's pretty much the same, right? We have this big N, and we have this such that for any natural number greater than that, f of n should be less than or equal to, and here we have c times g of n. And in this definition, we have, right, for some big N, for any natural number greater than n, f of n is less than epsilon times g of n. But the difference here is that, remember, in our definition of big O, like like the c was in this exist statement, right? The c was like right there. But instead, in this case, we've replaced it with for any epsilon greater than 0, right? So in the last case, like we got to pick c because we're proving an existence statement, and the way you prove an existence statement is by giving an example. So that means we got to choose c, like we got to choose what constant factor we needed, and it could help us. Like if g was really small, we could pick c to be bigger to make our proof easier. But in this case, we have to prove that this holds for any epsilon. So that, in other words, we can think of it like this. Basically, for any factor, any constant factor, at some point, g will just become that factor larger. So like, let's say you want to be like, oh, I want to make sure g is like, at some point, like I want to make sure that g runs 1,000,000 times slower. So then you pick epsilon is equal to like 1 over 1,000,000, and then there's some natural number above which f of n is less than 1 over 1,000,000 times g of n, right? And if g of n is the runtime of some program 2 and f of n is some runtime of program 1, that means f of n runs literally 1,000,000 times faster, right? And this holds for any epsilon, so that means that this holds for any factor. Like at some point, f is going to run 1,000,000,000 times faster. At some point, f is going to run like 1,000,000,000,000 times faster, right? And so this really characterizes the relationship of like f runs faster than g, right? Because like any amount that you want it to run faster, like at some point, at some input size, like it's going to be running faster. So that's sort of the intuition behind that definition. There's also a definition for like f is greater than g, right? So like p2 runs like much faster than p1. But we'll leave creating that to you on the problem set because it'll be a good exercise in sort of like making sure you understood these definitions and trying to create another one. So before we do a practice problem with this, I want to give an alternative definition that's usually a little bit easier to work with. It's going to include something called limits, but I'll explain what limits are in case you haven't really heard of those before. So again, so for functions, f and g, natural numbers to positive reals, we say f is little o of g if the limit as n goes to infinity of f of n over g of n equals 0. And I'm going to explain what the limit means, but just to give some intuition here, like a limit is basically saying like as n goes to infinity, what is the value of this quantity? And this is basically saying as n goes to infinity, this quantity right here just gets closer and closer and closer and closer to 0. And the only way that can get closer and closer to 0 is if g just gets like larger and larger and larger and larger and larger, like an increasingly amount larger than f, right? And that's sort of what we're saying, right? Like we're saying f is much, much smaller than g. So asymptotically, that's what little o is saying. Little o is saying asymptotically f is much smaller than g. And that's also what this limit is saying, right? Because the limit is saying like asymptotically, as you make the input size really, really big, this quantity right here basically goes to 0. In other words, g gets much, much bigger than f. So right now, I've written out the technical definition of a limit. The technical definition of a limit is, right, for any epsilon greater than 0, there exists a big N such that for any natural number greater than that, f of n over g of n is less than epsilon. And if you've heard of limits before, you can like check to make sure that I did that correctly. If you've never heard of limits before, no worries, don't sweat it. You can just take this as sort of the definition of a limit, but it's not really that important to understand. I think the important thing to understand is that, like, is it clear that this is the same thing as definition 6? And it is, because actually all these quantifiers are the same. Definition 6 starts with for any epsilon. This also starts with for any epsilon. Then this says there exists a big N. That, this also says there exists a big N, such that for any natural number greater than that, again, we have for any natural number greater than that. And then, so we just have to make sure that these last two statements are the same, right? And this first statement is f in definition 6 is f of n is less than epsilon times g of n. But since g of n is a positive quantity, we can just divide both sides by it. So this is equivalent to saying f of n over g of n is less than epsilon, which is what we have in our limit definition. So we can see that these two are the same thing. So the definitions are the same. And the reason we want to work with this limit definition is it'll just be a little bit easier to use. We know like some like L'Hopital's rule and some other things that might make it a little bit cleaner. Great. So now let's apply little o. And what we're going to prove is that for any k, n to the k is little o of 2 to the n. So what does this mean? Well, this means if n to the k is the runtime of some program p1 and 2 to the n is the runtime of some program p2, and then regardless of what k we choose, as long as program 1 runs like in polynomial time, right? That's sort of what we're saying here. It runs in some n to the k for some polynomial. Then if p2 runs in exponential time, like p2 is always way, way, way slower. So this means like we always prefer a polynomial time algorithm over an exponential time algorithm, which is, I think if you've never seen like asymptotics or runtime before, this is sort of like a surprising result. It means like it doesn't matter what the degree is on the polynomial. Like that's always better than any exponential. Great, so we'll prove this by induction and we'll use our limit definition. So in other words, we're going to prove that for any k in the natural numbers, the limit as n goes to infinity of n to the k over 2 to the n equals 0. Okay, so let's do the base case. The base case is k equals 0, so we're considering the limit as n goes to infinity of 1, right, because n to the 0 is just 1, over 2 to the n. And we will just prove this with the definition. So now we need to prove like for any epsilon that this statement is true here. I'm going to just erase some of this. so that we can see a little better, we need to prove for any epsilon that this statement is true, right? So fix some epsilon greater than 0 and set big N equal to the log, and in computer science we always mean log base 2, but we don't actually write the base 2, of 2 over epsilon. So now, let's say, so now we have to prove for any n greater than this big N, right? F of n over g of n is less than epsilon. Well, so again, we'll fix some little n greater than big N. Then f of n over g of n just equals 1 over 2 to the n, right? And since we know that n is greater than, little n is greater than big N, this implies that 2 to the little n is greater than 2 to the big N. And therefore 1 over 2 to the little n is less than 1 over 2 to the big N. And 1 over 2 to the big N, if we substitute this in, is just equal to 1 over 2 over epsilon, which equals epsilon over 2, which is less than epsilon. So we've successfully shown, right, for any epsilon, because we fixed some epsilon greater than 0, we picked some n, big N, to show that it existed, and we showed for any little n greater than that, the relationship holds. So that shows the base case for k equals 0. And it's a good sort of example of applying the definition of little o. So now we need to show the inductive step. So for the inductive step, assume the limit as n goes to infinity of n to the x over 2 to the n equals 0 for any k less than or for any x less than or equal to k, right? And we want to prove or want to show, WTS, that the limit as n goes to infinity of n to the k plus 1 over 2 to the n equals 0. So we're going to use a rule called L'Hopital's. So let me just write this limit out again so we have a little bit more space. And L'Hopital's rule is a multivariable calculus rule that says, like, if you're evaluating this limit and both the denominator and the numerator go to infinity, so in this case, right, 2 to the n as n goes to infinity, that goes to infinity, n to the k plus 1 as n goes to infinity also goes to infinity. So since these things both go to infinity, we can just take the derivative of both sides, take the limit again, and that will give us the limit. I think it's okay if you don't like super understand this rule. It's more just for completing this proof. It'll be less important for the problem set. So we'll take the derivative. So again, we need to apply the limit to the derivative of both sides. So the derivative of the top is k plus 1 times n to the k, and the derivative of the bottom is the natural log of 2 times 2 to the n. And now we apply another limit rule, which is like the limit. Let's say you're taking the limit of some like function g, right? Then the limit of some constant c times some function g is the same thing as just that constant c times the limit of the function g. So in other words, k plus 1 over natural log of 2 we can just pull out because it's a constant. So we get k plus 1 over the natural log of 2 times the limit as n goes to infinity of n to the k over 2 to the n. But our inductive hypothesis says we know that a limit as n goes to infinity of n to the x over 2 to the n equals 0 for any x less than or equal to k. So this quantity right here must be 0, which means that this comes out to 0, which completes our proof, right? Because now we've shown that our desired limit equals 0. And so this must hold for all k. And so then for all k, we know that n to the k is little o of 2 to the n, or in other words, polynomial is much, much smaller than exponential. So that's an introduction to lots of different asymptotics and ways of thinking about calculating and comparing the runtime of functions.